Hello. This is video 33. And we've looked at an example of red-black trees, but we haven't really talked about them in very much depth at all, have we now? I'm going to call this red-black tree Q&A, questions and answers. And I may put myself on the spot. I hope I don't ask myself questions that I'm not able to answer. That would be embarrassing, wouldn't it? But that possibility is not excluded. Question 1. What's a red node? That's Q for question. Well, it's a node that's red. Next question. Well, let's be careful though. In the context of a red-black tree, what makes a node a red node? What role does it play? All that kind of stuff. No, I'm not going to write all that down there. It's a node that's in the same red box as its parent. I'm going to try to be efficient with board space so I can get several questions on here before I have to erase everything. A red node is a node that's in the same red box as its parent, which begs the question, okay then, well, what's a red box then? A red box, if you remember, we actually got here sort of in a natural process following through from binary search tree to balanced trees. Oh no, what can we do? My binary search tree is degenerated into 2, 3, 4 trees, and a red box is a 2, 3, 4 tree node in which instead of storing the 3 data values in an array, we store the 3 data values in a mini BST. I think I invented that term. Maybe I should get my name associated with that. In an England mini BST. So there you go. A red node's in the same red box as its parent as part of the little miniature tree. That's part of the answer. I'll do bullet point answers. A node with a red incoming arc. I'm referring to my picture. My picture is part of the text about red-black trees. A node with a red incoming arc. And I think I drew that picture correctly, and if I did, then inside the red boxes, the only arrows you saw were red arrows. Those are the red incoming arcs. There. That's sufficient for now. We can come back and talk about that later if we need to. Question 2. Let's see if we get another softball pitch. Although I've seen some softball pitches that go pretty fast. What's a black node? And sort of implicit in that question is, how is it different from a red node? And this is also going to have a multi-part bullet point answer. A black node is a node that's the root of a mini BST within a red box. Let me see if I can remember that long enough to write it down. A node that's the root of an England mini BST, but I'll just write a mini BST. And I'm going to have to use another line inside a red box. Well, if we match it bullet point per bullet point, you know what the next one's going to be. It's a node with a black incoming arc rather than red. A node with a black incoming arc. So if we were to contrast compare, a red node is merely a child inside a big red box. It's a child of a parent that's also inside the big red box with it. The parents have black incoming arcs, and they are not inside a red box with their parent because the black arcs are the ones that connect the red boxes to each other. Okay? Now, a note before we go one step further. The root of the entire red-black tree, RBT for short, red-black tree, will always be, let's pause and think about this for a second, reflect. The root of the entire red-black tree, it's got to be one or the other. We don't allow any pink nodes or green nodes or anything. It's either got to be red or it's got to be black. Well, if it's red, it would need to be in the same red box as its parent, except think about this. If it's the root of the entire tree, it doesn't have a parent. It is the parent of all parents. So it's going to have to be black. The root of the entire red-black tree will always be black. And a strange side effect of coloring nodes red, coloring black, whatever, depending on the current situation of the structure of the tree, occasionally you might have the special case where you turn the root of the entire tree red. How could that happen? Well, maybe the red box at the very top of the tree, we've seen this happen. The red box at the very top, Sally sells, she sells. The red box at the very top of the tree might split if it's already got a full mini BST with 3 nodes, red child and a black child. When it splits, technically what's supposed to happen is the root of that mini BST is supposed to become a red node and rise to live with its parent in a red box. Now, if that happens to the root of the entire tree, it cannot rise and move in with its parents because it doesn't have a parent. But your algorithm that's doing the split operation to split a red box into 3 red boxes, that might very well try to color it red. So I'm going to put parenthetically here, ... The root of the entire red-black tree will always be black, and if it accidentally isn't, accidentally, isn't, because of the way you've implemented your algorithms to do the split of the red box at the top of the tree, forcefully make it black. Paint it black. Stone's flashback. Forcefully make it black in the, what's going to be, what is it, the public wrapper. Of who? Print debug? No. Remove? No. We don't even have a remove function. Public wrapper of, you got me, the put operation of put before going back to the main program. Before returning to main. In other words, this is a special case of a boundary condition for our red-black tree structure. It's possible that your algorithm, your elaborate, insightful, genius algorithm that is structuring the tree and restructuring the tree and balancing things around and all that stuff, it might have colored the root of the whole tree red. You don't even have to check and see. You can just say, set the root color to black before you return to the main program from your public wrapper for the put function, because it's got to be black all the time. So there's not even any point to test to see if it's already red or black. Just say the color is black before you go back to the main program. And that's done before, of course, before you return true or false, whether or not the put was successful. So this will be not the absolute last thing you do, but it's the next to the last thing you do. It's certainly after you call your private overload that's doing the actual operation. That was a much longer note than I anticipated. Do I need another node here? Oh, yes. A new node inserted at the bottom of the tree Well, that's the only place it can be inserted, so that's redundant. A new node inserted at the bottom of the tree. Will always initially be red. Now, don't take my words on this as gospel. Let's think about this and see if we can figure out why that should be the case. We're always, remember 2, 3, 4 tree, we were always inserting a new data item in an existing 2, 3, 4 tree node that was already there at the bottom of the tree. How can we even ensure that that's possible? How can we make sure that's happening? That's why we do the split in the first place. We split to make room for new data values that get inserted at the bottom of the tree so that everything can stay nice and level down there at the bottom. We pull the same trick with the red boxes. On the way down the tree, if we see a full red box that's got a mini BST with 3 nodes in it already, then we split it on the way down. It could be several generations before we get to the bottom of the tree. But what that does is ensure by the time we get to the bottom of the tree, there will be room in an existing red box for the new data value that we're inserting, so it will be red. Initially, it lives with its parent down at the bottom of the tree inside a red box. So that does make sense. That's not just an arbitrary rule tossed out there. 1, 2, I barely have room for question number 3. Pardon me. Question 3. Where's question 3? How is an RBT different from a BS? Well, let's talk about the implementation. How is the, make it sound as if there's only one way, but there's lots of ways. How is the implementation, in general terms, of an RBT, red-black tree, different, and I'll abbreviate so I can put it on one line, different from a BST? How's our implementation file going to be different if we take a global view? We're not looking at individual nodes right now. How's the implementation going to have to change? Only the put function. That's what's going to be different. Only the put function. Now, that might seem like that's too good to be true. First of all, be careful what you wish for. Too good to be true. That one function is going to change dramatically. It's going to become most of the lines of the program when this is implemented. But let's think about that. The put function is responsible for, on the way down, looking to see if a red box needs to split and then splitting it before it moves on. And then it recursively goes back and forth, left and right, implementing our order log-based who of n search for the node or the place where the node goes. Then it gets to the bottom of the tree, and that's where it inserts it. And then on the way back up, it actually has to look behind itself and see whether or not we need to rebalance a crooked or a straight line mini BST that's too long. All of that takes place within the context of the put function. So look what we got here. Similar to the way the ordered list was really just a new version of the put function, and everything else stayed the same. Same thing here. Red-black tree, we could do that by having a new version of the put function that takes into account all the colors in red boxes and all that sort of stuff. So it's going to be dramatically more complicated, but all the other stuff is still the same. Since we still got arrows that point left and right, we'll still be able to wiggle down the tree for what we're looking for, just like we did in the binary search tree. The print debug will need a tweak. The print debug, I'm going to require that we also print out what the color of the node is as we're going through our tree with the print debug function. Okay? We didn't get very far, but that's a board full. And rather than make you watch me erase the board, I'm going to stop the video and erase the board, and I'll see you online.